So, Bowden,
Hello. Hello.
hey, you're consistently online these days. Started
Yeah.
liking it, huh? Let's see. How was the homework, Bowden?
I thought it was all right, I guess. Yeah, it wasn't too bad.
Okay, good. Hello, Jeremy.
Hello.
Okay. How was the homework, everyone? Reasonable? Jeremy, you don't seem very
It was
excited.
wasn't.
It was
I
hard?
I mean, I got an answer, but like, I think my issue with some of these like questions in all my classes is just like, I know I knew how to do it, but reviewing, like, I don't know, there's just like missing links still that I'm kind of like figuring out as like the homeworks come along. So it's all right.
The example that we did in the class, when you go over it, it didn't very help, is it?
What? I'm sorry.
Like it was based on an example we did in the class, but that did not help much. That's you're saying?
It was fine when we got it down to the, I guess the phi cross r over r cubed, like you mentioned that we had covered it before in the last semester, which obviously was like just recent for everyone else, but I was trying to figure it out, like trying to find something on it.
Okay. Reasonable. So that's the second problem then, right? Not the.
Yes, yeah. first one was fine. That one was easy. So
Okay, good. Yeah, I was more interested in the first one. Yeah. Okay, that's understandable. Christian, Curtis, went well.
Yeah, I was a little bit confused on the second one. It seemed like in class you wanted us to find the vector potential, but then in the problem you asked for the total dipole moment. Total dipole moment.
Oh, yeah.
yeah,
That's-
that
So I was a little bit confused, so I just found both. So I did the total dipole moment similar to how we did the first problem, just assuming that it was a series of circles, and then
Yeah.
and then I tried to calculate that integral for the vector potential too, but I didn't know if that's what you're asking for.
No. Actually, looking back, I think I did ask only the dipole moment because it's simpler, significantly simpler, and the field is significantly harder. But then I had in mind that I was asking at the center of the circle, which makes it very simple. So yeah, since it's a confusion, I can quickly go over it very quickly. I would like to start. So yeah, so the point is, so you have the circular wire, right? That's the radius r, and at this point there is a dm, which is pretty much lambda times ds, but ds itself is lambda times r times d phi here, correct? Or help here. Lambda times r times d phi, and in the direction of phi hat. Is that correct?
Yeah.
Okay. And the total dipole moment is significantly easier. I think that's what, now that you point out, I meant to ask. And that is simply lambda r d phi, and then I integrate it from 0 to pi. Right? So let's say this is angle phi, 0 to pi, and that's phi hat. Okay. And so that's, let's see, lambda times r, 0 to pi d phi. Phi hat, recall, is minus sine phi in the I direction plus cosine phi in the j hat direction. Now that's equal to, I think, it's sine phi integrated from 0 to pi contributes. Cosine phi actually 0 to pi goes positive and negative, right? So that will be equal to 0. So this one contributes, so it's lambda r integral of sine is cosine I hat cosine phi evaluated from 0 to pi. That's I lambda times r. Cosine of phi is -1. Minus of cosine of 0 is +1. So it's I hat times 2 lambda r. Yeah. I think that's all I was asking. Yeah. If you do decide that you want to, I think when I was doing it in the class, what I had expected was I was asking for the vector potential right at the center of the circle. In that case, there is a simplicity because then dm crossed with r, let's say vector r over r cubed, correct? Then this distance is simply r. So this is dm crossed with point r will be minus r hat, and this is simply r squared. One r from the top, one r from the denominator, and we only have to worry about that angle. But let me leave that at this. If it is at the center of the circle, that can be done. Let me say that and stop. But yes, now that you remind me, it's just this one I was asking. Just because it is significantly simple, I didn't want to ask a hard question. So yeah, my comments in the class probably threw you off, Jeremy. Your point is right. Yeah. Okay.
Yeah.
Christian, does it help?
Yeah,
Probably.
it does. But then could you
Mhm.
solve it in a similar way for the total dipole moment without bringing in lambda? Just using basically like the physical interpretation, like how we solved the first one with the loops. I mean, if you're envisioning a torus, then you can have a series of circles. So, you know, I like the current times the area would just be pi a squared. And then you have, you know, the series of circles in a semicircle. Can you do it that way still, or is that not allowed?
Let me see if I'm understanding your question correct. So you would like to say that, so this is the torus you're talking about, right? So this is a torus. Is that your point?
Yeah, and the question, it was a half torus.
Yeah, so this is the, right?
Uh-huh.
Right. Yeah.
And the
And
current
yeah, and this is okay, maybe I don't remember the question at all. So yeah, M will be equal to I times A, where A is this area,
right.
right? And phi hat, correct? Or dm would be, so that's for single circle. So dm has to be the number of terms, right? Yeah, I think maybe that's what I meant. Yeah.
Right, which
So,
you had said that the number of turns was n and that they could be approximated as circles.
yeah. So m, so, yeah. So dn, sorry, n will be. I think yeah, lambda there is. Help me. So give me a second. So dm over ds is equal to lambda, right there. Lambda times phi hat. And so this is m times the number of turns, let's say dn, over, let's say number of turns, total number of turns over ds is lambda times phi hat. Okay, so let's say this is this. And dn over ds is small n. Does that help? Isn't that correct? M times n will be lambda times phi hat if you want. You wanted a connection between lambda and n, right?
Oh, no, I was saying for the total dipole moment without bringing in lambda, because you have the area of each circle essentially.
Yes, but that is exactly what I'm saying here. So m is this. So now I want to talk about a small element here, right? So suppose I have a small element. I need to know how many magnetic moments I have per unit length, correct?
Mm-hmm.
So that will be equal to m times, let's say, capital N, right? That will bring in this. So my dm would be m times dn, right? Where this is the total number of turns per, or total number of turns in that infinitesimally small region. So I have to define by lambda. So this is dm by ds would be dn by ds. Does that help? With the direction. Yeah. Right? So this has become my lambda, if you notice. If earlier I did it in terms of lambda, I just have to replace lambda with this quantity.
Okay.
Does that help? Okay, maybe let me do this a little more formally. Okay, so let's start with this. Yeah, go ahead.
Well, I was just wondering, so when you integrate over that, do you get an extra factor of pi, like from integrating over the half circle? I guess was, I'll let you, I guess, go through with it because I just had a small confusion when I didn't.
Maybe. Okay, so let's see. So I will have to integrate this. So my dm would be equal to IA times phi hat times dn. But I want to do this with respect to d phi, integrate it with respect to d phi. So I will put this as d phi times d phi, just multiply and divide by that, correct? And this is number of turns per unit angle. But I know number of turns per unit length probably, so I'll multiply and divide by r. Yeah, you will get an additional pi because of this area, I think. We'll see. Okay, so that's pi. Sorry, what did I say? I want to put an r there, right? So r there, and there is an r here. So what we have is total magnetic moment m when I integrate. So it's r I a, and this is number of turns n. So integral of 0 to pi hat d phi, right? Which I did earlier and got a minus 2i for that. So using this form, I would get minus 2i hat r I a n. Is that correct? Yeah.
You scroll down a little bit, the
Oh.
camera, please.
Sorry. Yeah, you got almost. Yeah. Does that make sense? Which is the same as lambda. If I were to connect it with lambda, lambda is IA times n. Yeah. Right, if you want to connect it with that, so lambda in my first derivation is magnetic moment per unit length, so that's n. Does that help?
Yes. Yeah, it does. Yeah, I didn't see the I hat coming out when I was doing the homework, but I see that all the vertical contributions cancel.
Yes, vertical part. And why does that happen? Because here there is this component coming in, and when it is at the bottom, it is opposite, right? Yeah, graphically, you can see that very clearly. Oh, I was showing you properly. Yeah, I think graphically this comes out. It should be visible very clearly. So here, it is upwards, the vertical component cancels the right opposite. Okay.
That helps. Thank you.
So yeah, so that is an exam and on Friday. So I think these kind of problems, the magnetic moment addition should be reasonable to ask, right? So I can give a curve, so let's say a square or this time it was a circle, semicircle, quarter circle, let's say, semicircle, quarter circle, or any kind of that structure. I'll put a string and then you should be able to calculate the dipole moment and the first problem also. So that's a good candidate for an exam. So just, any other questions?
Is our exam going to be in person?
Yes, is that okay?
Yeah.
That should be fine.
Yeah, I think it's good that you guys should at least see each other once in the whole semester. I should also see you guys.
Can we get a reminder on the room just in case?
410, 410. Okay. It is the same room, Jeremy, where you took the first class. It's the same.
Okay.
It's exactly the same room, but its entrance has changed. It is no more entrance is no more the place where it was. The structure has changed a little inside.
So
But
it's
just, yeah,
neighbors then, right? Just top floor.
yeah, top floor on the corner. Its entrance, actually one of the entrance is still there, but one of it has been closed. It used to have two entrances, if you remember.
Yeah.
So the one of them still is existing. Curtis, is that good? Would you be able to make it?
Oh yeah, that's fine.
Yeah, how often do you get out, Curtis?
I usually like walk every single day, so I'm pretty out pretty often.
Okay, no, or maybe I should say, do you go to the grocery store?
Uh, occasionally, yeah, like once or twice a week.
Okay, maybe, yeah, maybe then I shouldn't be making you guys come out. So, yeah, okay, I'll take a final count on, tell the final verdict on Monday, let's say. Okay. Yeah. Okay. So, we want to, any other questions, comments? So we want to start something slightly different, but basically make it more general. But the idea is the same. Let me see. So first of all, there's homework 7. Midterm 2. Is on Friday. And based on what I see, it seems like it is getting better. But yeah, since you guys say you're not started getting out, so yeah, let's say tentatively in class, like in person, right? That's tentative. On Monday, I'll try to give you a more certain. Okay. Yeah. And it's good to expect that there will be one of the question on the, I said on the elliptic integrals, the issue we had in the class. So that will be on that. Second one, I think I'll ask on magnetic moment. If it is in the class, I'll make it short. It will be only 3 or 4 questions. And then we are going to be doing Lorentz transformation, so special relativity. So that's what comes off my head immediately. Okay. Notice that we have Maxwell's equation in the complete sense, not, suppose we don't put in the condition of statics. Maxwell's equations, the full scope will be dotted with, let's say, epsilon naught E. I can write the epsilon naught on the right also, that's perfectly fine, and that's charge density. And similarly, the divergence of the magnetic field is equal to 0 actually, because there is, like we have charge density is how many charges, electric charges are there. There are no magnetic charges, so that's 0. So that no magnetic charges means there are no north poles and south poles separately. They can combine together and have dipoles there. We have talked about a lot, but they don't exist as a north pole alone. Curl of an electric field is equal to negative derivative of the magnetic field, time derivative of the magnetic field. That's Faraday's law. And we have curl of the magnetic field if you want. So that's H. Let me write this in terms of B. So B over mu naught is equal to time derivative of epsilon naught E cos J. Right, often you write this as D and this is H, and that's perfectly okay. One should realize that when you do the statics, this term is not there, right? And in fact, before Maxwell, this term was not realized at all. Until Maxwell came over, these equations were written without this. Right? And it was Maxwell who introduced that term. And the moment you introduce that, one comes up with a wave equation for electric field. So let me talk about that. So we have discussed this here and there before, but let's do this again. So let's take the cross product of this term here, or the cross product of the either of the two equations that I have written in the second line. So let me start with the second one. Typically, it is done with the first one. So let me do it with the right hand side equation. So del cross with del cross B over mu naught. Let me take the mu naught onto the right side. So if I take the curl on one term, I have to take the curl on each of the terms. So that's equal to mu naught times epsilon naught times time derivative times the curl of the electric field. Notice curl and time derivative goes through each other, so that's perfectly fine, plus curl of J. Substitute the curl of the electric field from the third equation here, or this equation here, into this, and what we learned is, and expand this curl, double curl if you want, is given by minus, let's see, hold on, not minus, right? We have del gradient of the divergence of the magnetic field minus B is the free, so that's here, Laplacian of the magnetic field. That's just an identity, vector calculus. We have used this many times. And this is equal to mu naught times epsilon naught. Put in the curl equation, so that's minus second derivative with time of the magnetic field, and that's plus curl J. The first term is equal to 0, so that's Z. So what we have here is, if I were to write it onto the left-hand side or onto the, let me write it. Yeah, minus del square plus mu naught or magnetic field is equal to del cross J. So what it says is that if I have a current, then this will produce a magnetic field which satisfies this equation. Earlier, all the time, we didn't have this time dependence. We were talking about static situations. Right? We had the Laplacian of the magnetic field, and how was the magnetic, currents creating the magnetic field. But now we are talking about the time dependence also. And it seems like anywhere where there is no current, this equation is satisfied. And this equation should ring a bell. Any idea of what is this equation about? Like suppose I set this equal to 0. Let us say if J was equal to 0, let me write that down. if j was equal to 0 in some place, in any area, wherever j equal to 0 in a region, right? That means to say, if you're outside the current wire, anywhere where there is a wire is not there, j is equal to 0. And in that situation, we have the Laplacian of the magnetic field is equal to mu naught epsilon naught times time derivative of b. And what does that equation suggest? You have seen this equation before by any chance? Anywhere else? Remember, this is a partial derivative with x, partial derivative with y, partial derivative with z. If I were to say everything was in one direction, this in one dimension, this is in 3 dimensions. So let's say in 1 dimension, this looks like partial derivative with z, let's say, if everything is moving in z direction. And let's say instead of magnetic field, I have some other function f, just to give you a feel for what this is. And this is equal to, let me write this f 1 over v square so that the dimensions, suppose I were to say this is very, this is a slight generalization of that equation, let's say. Now, if this equation doesn't make sense, have you seen this before? If not, we will try to think about it. Does it ring a bell? No? Okay, this turns out to be a wave equation, by the way. Any function that satisfies this will be a wave. So let's see, how do you see that? So let me elaborate on that. So if that is the case, let's say you have a function f, this is z and t, right? There are only 2 variables. Let me say that this is of the form z minus vt. Or actually, let's take an example. Let's take an example. Let's say this is exponential of minus z minus vt square. Okay. Let's do the derivatives. F by dz is equal to the same exponential, but then so this is exponential of minus z minus vt square, and then you take a derivative, right? So it's a minus of 2 times z minus vt, and finally take the derivative with z, right? So that's what you get. Is that clear? That's the derivative with z. What about take a derivative again with z? So that's d square f over dz square. I can hit it in the first place, or so there are 2 z's now, right? So if I hit it in the first place, again I'll get this. So this is exponential of z minus vt square. So that's will be minus 2 z minus vt square, because I take the derivative again. And the second time I'll hit this z, so that's just a minus 2. So that's minus 2 times exponential of z minus vt square. Right. And let me not expand this further. Let's just, I just want to do an example here. What about time derivative? This is df by dt is equal to, do the same thing, but this time I have to hit it with the time. So exponential of minus z minus vt square minus 2 times z minus vt. But eventually I have to take the derivative with time, so there is a minus v there that shows up. That's the only difference, the minus v that extra has shown up. Do the second derivative with time, and it's still in the both space. Second derivative will be very similar, minus z minus vt square minus 2 z minus vt. Again, you bring in a minus v, so it's a whole square. And when I do the derivative here, this time it is there is an extra v there, right? So this is plus time, right? Sorry. So there's a minus v, there's another v here. So there's a 3 minus signs. That gives you a minus and 2v squared. Which, if you notice, if I were to pull out a v squared, that's exactly equal. That's exactly equal. If I were to pull out the v squared, that's exactly equal to second derivative of df by dz squared. So that what that means is that this function satisfies the differential equation. That means it's a solution. But there's nothing special about that exponential. If you had put f is equal to sine of z minus vt, that would have also satisfied that. Okay. If you had put exponential e raised to I z minus vt, that would have also satisfied that. And you can put any function of the form z minus vt, and that would have done the job. In fact, exponential function that we showed, that actually looks like that. That's a Gaussian. And if this was z, and this is exactly equal to z equal to vt, that's actually the curve there. So what that means is that this is actually a wave, like this can move. The only thing that happens is that this position moves with time. I think of a tsunami kind of a wave, right? There's a bump there, and that actually moves with time. So this is a very general solution for a wave equation. And more importantly, the v that shows up there is actually the speed of the wave. Whenever we think of a wave, by the way, what's the difference between a wave and an oscillation? Like a simple harmonic motion that we talk about, and so we have a spring attached to it. So that's a simple harmonic motion, and a wave is basically a simple harmonic motion at each point in space, and they are all connected in the sense that if this one moves, the second one, the next one will also move. Right? So it's in a sense a lot of oscillations all over the space and time. So the oscillations is something happening, a periodic thing happening in time, and when that same thing happens in all space, so that each point is connected to the next one, that's a wave. And the equation of a wave is as I gave there, and its velocity. So the velocity of a wave is exactly when you think of an exponential curve and it's moving, we understand that the energy moves with that, right? So that's what it is. So it seems to suggest that for the implication here is that we have a magnetic field satisfying a wave equation right, with its speed, which we'll call it the speed of light, c having the definition of 1 over mu naught times epsilon naught. And c is 1 over mu naught over epsilon naught. Notice it does not depend on any property of material. These are property of the vacuum if you want. They are perfect constants, like you go to anywhere in space, to our knowledge, this is not going to change. No property of the medium coming in. It's a perfect constant. And to our knowledge, C does not depend on any other physical parameter. So in that sense, it's a constant. But the bigger statement is that magnetic field behaves like a wave. Like that means whatever B is, it moves from one point to the other, and it can actually maybe carry energy. And we have already seen that electromagnetic wave has energy and momentum associated with it. So its speed now is c. And notice that Maxwell gave this in between 1860 and 65. I think probably 62. I think if I remember right. I'm not sure. So he gave these equations in 62, and immediately it was understood that you can transfer energy from one point to the other at the speed of light, and within 10 or 20 years, I think Hertz, I think it was 18, it's anywhere between 75 and 85. Let me be very safe. Let's say 1885 Hertz in a laboratory showed that, think of a classroom of this size, showed that you could send a signal from one point in the room to the other point in the room. And this was the first radio wave. And it was realized that the wavelength of this wave can be anywhere between 0 to infinity. And either you have a radio wave or a microwave or a light wave, all those are characterized by the same equation, which is this wave equation. So that's good. So we have a wave equation, but that also led to another concern, and that's about relativity, and that's what we want to talk about. So we have a source of electromagnetic wave, the way we have seen it. Think of light as we see, and we know that light actually goes as a spherical wave, right? If there is a source, it will go away, and let's say that's your wave going outwards, right? So that's your electromagnetic wave getting thrown outwards, and let's say this is the direction z, and somewhere here observes it. So let's say this is the observer, and that's your source. Right? So light starts from here, and it is observed from there. Let's say this is being this event. I shouldn't say the observer here, right? It might be confusing. Let's say light goes from one point to the other. So there are two events happening. So that's 1 and that's 2. It starts from here, reaches there, and I put it along a line, horizontal line purposefully. It can go in any direction in principle. And let's say this is observed by 2 people. Right? One is at rest with respect to one, and let's say another person here is moving. So this could be in a car, right? So it's in a car, and that's moving with velocity v. And we know that this equation, so this is traveling at the speed of light, right? That's a wave now. And this, along this line, it is moving with speed of light. In fact, it's moving with speed of light in any direction. And that, according to this observer, will be x squared plus y squared plus z squared is equal to c squared t squared. What do I mean by that? This is just the radius of this. So this is the radius r, right? So that just means that r is equal to ct. Like the distance traveled by light in a certain amount of time is c, right? In all directions it goes at c, which means r square is equal to c square t square. That's what I wrote it as, x square plus y square plus z square is equal to c square t square. But if someone is moving, one would expect that the speed changes, right? If someone is moving and you measure the speed of another car, you expect the speed to change, right? That's Galilean relativity. So that would have said that if you're going in the direction of the same car as another, then you measure either a slower or faster speed. So, but according to what Maxwell says, this guy will also measure the same r prime. So r prime will be different. This distances might be different, but it has to be the same c. C seems to be very fundamental. It says that it does not depend on any quantity, so it cannot depend on the observer either. Right? There is no information about the observer in here, so that seems to be an implication. And then you would say, instead of, let's say, so that would mean, so going back from here, so that's r prime square is equal to c square t prime square. This is r prime is equal to c t prime. And that would mean this is x prime square plus y prime square plus z prime square is equal to c square t prime square. And both has to be, both equations has to be valid. That's what Maxwell's equations are telling. The positions can be different, but the speed has to be the same. But how can that happen? What kind of transformation does this? If you have to do Galilean transformation, it won't work. So let's keep this as our two required relations, and let's ask what transformation actually. Oh, I think I was out of the board a little. Okay, so I was writing. So what I had written here was that r square is equal to c square t square, and here r prime square is equal to c square t square. So that's r prime is equal to ct, that's r is equal to ct. So r is the distance it goes off from
The t for r prime is also prime too, right? It's not necessarily the same time.
That's necessary actually. It would because if so what? So let's do the following. So what Galileo said is that before we had special relativity, so this relative concept would have, since it's all in one direction, even though x and y are perpendicular, you would have said that y prime is equal to y, x prime is equal to x, and z prime you would say is z minus pt. That's what Galileo would have said. And t prime would be just t. But if you put this in here, so let's put this, let's start from, you should be able to start from here and get there, right? So this is x prime square plus y prime square plus z prime square minus c square t prime square is equal to 0, right? So that's our second equation. Let's put these quantities in. So that's x prime is x, so that's x square plus y square plus z prime is z minus vt square plus c square t square minus, right? That's equal to 0, and what we have is x square plus y square plus z square plus v square t square, right? And then we have minus 2 times z times v times t minus c square t square is equal to 0. But this whole quantity, because of the first observation, is equal to 0. So what we are getting is that v square minus 2 times z times vt is equal to 0. And that doesn't seem to make sense, right? So if I were to pull out this quantity, so there's a v times t minus 2 times z is equal to 0. How can this be 0? Either the velocity be equal to 0, or this because t and z are variables here, you cannot put conditions in here. So it doesn't seem to make sense. So right, it doesn't. It's not compatible. That's the way to put it. That's not okay. So what one can ask is, instead of saying that, oh, this is all, there seems to be some interpretation issue, how does this work? You flip the whole problem around and you ask what transformation, what relative transformation between these coordinates will give you this equation to remain the same. You say that Maxwell's equations are correct. Indeed, these waves do look the same to both observers, but what is the connection between the coordinates that will lead you to that? So we will ask the following question. So let's say z prime, and we'll keep it linear just because that's easier. Let's say this is some constant e, which depends on velocity, times z. Let's say plus b, which depends on velocity, times t. Let me make it c times t, just so that dimensions are the same. C times t has the same dimension as distance, right? So a and b are dimensionless. So I don't know this. So these are the unknowns here. And let's say t prime is equal to, let's say, e of v times z plus f of v times c times t. Right? That's my unknowns, right? What Galileo would have said is that a is equal to, a of v is equal to 1. D of v actually would have been v, right? So it is v over c actually. E would have been 0 because time doesn't depend on position, and f would have been just 1. Right? That's Galileo. But now we keep it completely general and ask, under what a, b, e, and v is x prime plus y square plus z square minus c square t square equal to 0 in one frame, and the other frame, this should be consistent. They should look the same even after you transform to the other one. And we ask what is a, b, c, and f. And we'll come back and do that next time. So a quiz is, so try to get this a, b, e, and f. Try to derive a, b, c, and f. Basically what you want to do is, exactly like I did previously, substitute this in here and get some conditions on a, b, v, and f for the two equations to be satisfied. And that comes out to be very closely related to Lorentz transformation, but it won't be obvious that a and b, what a and b are. We have to put in some physics also into it to get the actual transformation. With that, I'll stop here and come back next time. Thank you.